In this series, we are looking at string-to-string library developed by Stanford University. In the previous 3 videos, we have looked at distance, similarity, and search functionality. Today, we are going to look at alignment. Now, string alignment, it's widely used in areas such as bioinformatics, DNA sequence alignments, and databases searching, etc. For example, the DNA is made up of 4 nucleotides. This thymine, cytosine, adenine, and guanine. Okay, these are generally represented by 4 alphabets: T, C, A, G. Now, different CNS are made up of the same 4 base elements, but they appear in different sequence. Okay, so in bioinformatics studies, we often study how similar or dissimilar two DNAs are to each other. So what we do is we have this pair of strings. For example, it could be TACG, ACGG. It goes goes like that. Then given those two strings, we'll align them first to study how much similarity or dissimilarity is there between those two. Okay. One second. Yeah. Now, so the alignment task, it's this optimal alignment between two strings. Now, here there are 3 things. One, when we do the alignment, we want to maximize the number of matching symbols. Okay, when we take an example, it will be more clear to you. So our aim is to maximize the number of matching symbols. But in order to do that, we need to make 2 compromises. Those are, sometimes we need to allow gaps and sometimes we need to allow mismatches also where necessary. Okay. Let's take an example. So there are a couple of different alignment techniques. Those are called this global alignment, local alignment, and then the longest subsequence and longest strings. We will see examples for all of these, and we will see how to compute them as well. Okay. So the first one, it's a global alignment algorithm. It's called this Needleman-Wunsch. Okay. So here we instantiate from this function, from this class, instantiate the function, and then so here we have 2 sequences, right? Sequence 1 and sequence 2. Then we want to do the alignment. So all we need to do is from this class instance, just call this function get alignment and provide the 2 sequences. Okay. So what it does is it does adjustment to both sequence 1 and sequence 2 so that we'll have the maximum number of matches. Okay. As I mentioned, while doing that, it has to allow some spaces and sometimes mismatches. Okay. For example, after aligning, so the first sequence, it looks like this. So as you can see, after G, it has inserted a space. And then we have the remaining 1, 2, 3, 4, 5, 6 characters. And the second string, it has introduced a space here. The reason it does that is because with this alignment, we have the maximum number of matches. So 1, 2, 3, and 4. See, we have 4 matches, but if to do that, we have to allow 2 spaces and we have to allow 2 mismatches as well. Okay. All right. This each instance of the class has multiple functions. For example, here we have this get alignment where we provided 2 strings, and then we can another function, this print alignment, which takes the aligned text and it will print the strings in this format. Now, a couple of other helper or utility functions. For example, plot pairwise alignment. It's similar to this function here where we computed get alignment. But this time, in addition to the get alignment, we also get the indices so that we can plot them. Okay. So it's still we are supplying the aligned sequences here. Okay. All right. So it's just taking the output from these functions. So the aligned parts and the aligned path, and then some metadata type of thing. We can give a title, sequence name, sequence 1 2 name, etc. Okay, so it produces this graph. It becomes a little easier to see. I mean, compared to here, we can easily see which ones are aligned, which ones are not. Now we can do more. We can also provide the colors, because here we have four four symbols and one additional character to denote the empty space. So here we define 5 colors. We are doing the same thing, but this time just applying this color dictionary, so that we can see these nice plots, so that we can easily see the alignments. All right, so that's the global alignment. Now the for the alignment, it works on complex these list of strings as well. Think of a scenario where we have a DNA sequence, but it has cut into chunks or small pieces, right? Now we want to do these pieces alignment. Okay, so yeah, the syntax is pretty much the same. This time it's more like each string is treated like one single entity. Okay, one single character. Each element or each string or word is not going to be broken. Okay, not going to be broken, and we are not going to add spaces within the elements of these words or strings. Okay. All right. So yeah, we call the same function, but this time with two lists. So this is the alignment we got, right? So for the second string, it has introduced a space at the beginning, so that we can have this ATT a match. Okay. All right. So again, we are trying to match the number of uh, we are trying to increase the number of matches, or optimizing for number of matches. All right. uh, again, the similar thing, if we want to do some plotting, we also get the alignments with the indices. Okay, and yeah, this is how it looks like. And then for the local alignment, as we saw in the previous algorithm for the global alignment, one, we are maximizing the matches, and we are compromising on two things. One, we are allowing some mismatches. Two, we are allowing some gaps, right? So in this algorithm, what we can do is we can do this weighted sort of alignment, right? So we can give a reward for alignment, let's say, and we can provide, we can give penalty for mismatches and gaps, so that with these three variables, we can have our scoring function. Okay, so in this Smith Waterman function, so these are the three weights we are giving. So if there is a match, we'll give a reward of 1. If there is a mismatch, or if we have to introduce a gap, these two are negatively rewarded or penalized. Okay, these weights you can choose depending on your application. You might want to completely maximize, or we might want to avoid mismatches, or okay, or we might want to avoid gaps. So here we have a long string, and we have another string, and again, string to string library, they have developed the APIs quite well. So the syntax for different functions is very similar. Okay, so again, from the class object, we call this function get alignment, and we provide the two sequences along with the weights. Okay, so we have the provided the weights when we instantiate the objects of the class. All right, so this is the alignment. And then obviously we can do the visualization as well using the plot function, using the plot pairwise alignment. All right, that's the one. And then the third function we are going to look at is longest common subsequence. Now notice that this is subsequence, not substring. Okay, so this is the mathematical formula, but when we look an example, it will become more clear to you. Okay, so let's say we have these two strings. We are looking for longest common subsequence. Okay, for example, let's take ABC from string 1. Let's see if we can find out this substring ABC in the second string. Okay, so we start X, Y, Z, T, A. Okay, here we have A. Then we can skip some characters. Okay, so if we skip W, we have B. So we have AB. And if we skip V, we have C. So ABC and ABC. That's good. But we were trying to find out the longest one. So let's see if we can find out ABCD. So from the second one, we can find out A, B, C, and if we can skip K, J, F, G, H, S. Yeah, here we can find it. So ABCD, 4. The length is 4, right? Let's see if we can find more. A, B, C, D, E. So we can find up to D in the second string A, B, C, D, E, but we cannot find E. Okay, so A, B, C, D, E is not an answer. And then let's try A, B, C, F, H. So A, B, C, let's say here we are skipping D and E. So A, B, C, F. Now let's see if we can find the same in the second string. So A, B, C, here we can find F and H. Okay, as you can see, we can find A, B, C, F, H. So as you can see, there are lots of ways we can find, but the algorithm, it will try to find out the longest common subsequence. So what it has written is, it found the length of the longest subsequence it found is 8, and it found multiple examples. Okay, not just one, but multiple such subsequences. So one is this ABCFH LUP. So ABCFH L. So here we have L, and then here we have LPU. So here we have P and then U. So these characters, they have to be in the sequence. They don't need to be adjacent to each other. We can skip some, but they have to be in the same sequence. Okay, so we can find even this one. So as you can see, ABC here, and we can find ABC in the second one with by just skipping 2 characters. So ABC is common for all such pairs. Okay, so that's what finding the longest common subsequence. All right, now we can do the same for sentences as well. So this time we have to token, we are still doing at the character level. Okay, if we do at the character level, as we can see, the and space are common to both. So probably that will come up. So here the longest common subsequence length is 19. So the and space, and then Q, we don't have, we have a Q here, U, I, C, K. Okay, so we can have the space quick, but that length would be, so 4 characters plus 5 characters, 9 only, but we are trying to find the longest one, right? So it has able to find even higher subsequence which is of length 19. So the space, it took I from here, and then BON. So from the second one, here we have I, we can skip VE space. So we have B, we have O, we have N. So this is the substring or subsequence it found, which has the maximum length. Okay, so I hope you understand what we are trying to find here. And then, so as I mentioned, we can do at the word level as well. So here, until now, we are doing at the character level, right? So we can do at word level. Obviously, to do that, we need a tokenizer. Okay, so here we are choosing a simple tokenizer, which will split the text. using this empty space. Okay, so we have a very long text. Okay, we have very long text, and then first we tokenize it using the tokenizer here, and then here we are computing the longest subsequence by simply providing the two tokenized lists. Okay, and this time here we have got the longest one, the length is 74. Okay, so here each word is treated as one element. Okay, so here we have one, VON1, and then Newman made major contributions to, up to 2. Then we have many fields including mathematics. So until this point we have everything common up to mathematics, and then from the first string we have to skip mathematical because we don't have mathematical here, but we have logic, and then from the second string we also have the logic. Okay, so including mathematics, logic, including mathematics. Why is logic skipped? Oh yeah, logic is skipped because as you can see here, this left parenthesis is part of logic. So when we do this tokenization, which is based on this empty space, so this whole thing is one word, right? So that's why it gets skipped. Whereas if you can see a measure, so from the first one here we have measure, from the second one measure, theory, and we have to skip functional because we don't have functional here. So it goes like that, right? So theory group and then theory, like that. So the subsequence length is 74, and each element is a word as opposed to a single character. All right, and finally longest substring. So it is easier to understand substring once we understand the subsequence, because in substring all the characters has to be adjacent to each other, so we don't skip any characters. All right, yep. So here we have two strings, and then we are trying to find the longest common substring. All right, so if you look at these two, so it found out the longest substring is dreams and length is 8. Let's see if we have more than that, if we have bigger substring than that. So here we have dream, and then here we have dreams. So dream, that would be only 5 characters, but it's saying, okay, it's counting the empty space also. So here it is saying dreams, that 6 characters, 1 space on the left, 1 space on the right, and here we have the dreams with 1 space on the left, 1 space on the right. So those 8 characters, that's the longest substring we have. Dreamers would have been a bigger one, but the second sentence, it does not have the subsequence dreamers. Okay, all right, and then we can do at the word level similar to what we did here. So here we are using the tokenized text to do the same at the word level. All right, so here we are using the tokenized strings, and this time the longest common substring length is 14. And if we look okay, let's do one thing. Yeah, let's copy these two. Okay, so here we have nuclear physics. Okay, let's see. Nuclear physics and quantum statistical mechanics. Yeah. All right, so this is our string 1 and this is our string 2. This looks like a good possibility. Let's see how many words we have matching. So one Newman made major contribution to many fields, including mathematics. So until this point, we have the match, right? So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's about roughly 10 to 11. But we have found, I mean, there is another longest substring which is of length 14. So let's have a look at here. So nuclear physics and quantum statistical. Yeah, so it start from here. So we have this nuclear physics and quantum statistical mechanics, economics. Uh, sorry. So we have this string and economics, game theory, and general equilibrium theory computing, which we also have in the second string, which is, yeah, from here, if you can see from here. So we have this nuclear physics, quantum statistical mechanics, economics, game theory, general equilibrium theory, and computing. So until this point, we have the same substring in both the strings. Okay, hence the longest common substring is this, and its length is 14. Okay. Um, Hope you understand. The finding common subsequence is the trickier among these four. But I hope these two examples help you understand how we do that at the character level as well as at the word or tokenizer level. Okay. That's all for this video. Thank you very much.